Hello, this is Solutions to Homework 7. So let's begin with problem 1. Problem 1 talks about a mass that is sliding on a frictionless incline. Let me draw the incline. And that's angle theta, and it's given to be equal to 30 degrees. We have a mass m sitting on this, and it moves a distance d parallel to the incline. That's d. What are the forces acting on this mass m? We are told this is frictionless. Gravity acts on this downwards. That's mg. Normal force acts on it perpendicular to the surface. That's normal force. There is no force due to tension, and since it is frictionless, we don't have a friction either. And there is no spring attached to this. So there are two forces. We point that out by writing Newton's law. Mass times acceleration is equal to mg plus the normal force. Let's begin with part A in the problem. So it's part A. The work done by the force due to gravity is equal to mg remains the same. So we have the force due to gravity is mg dotted with the displacements at each instant. That's dr. This is initial to the final, and the path is along the incline. Mg remains a constant. Once mg comes out of the integral, the displacement is simply, if you add up all the tiny displacement, it just comes out to be the total d. So this is simply mg dotted with d. It's a simplification that happens for the gravitational force, which is constant. To have a diagram, we have the displacement d here. That's mg acting downwards. And the angle between them, if this is angle theta, we can complete the triangle, and this will be 90 minus theta, so that will be 60 degrees. So we have seen the idea of dot product. We have work done by gravity be equal to mg, the magnitude of the force mg, the magnitude of the displacement d, and cosine of the angle between them, that's 60 degrees, which is 90 minus 30, so that's 60 degrees. So that's equal to mg is 25 into 9.8. And d is 10 meters. And that's cosine 60. That comes out to 0.8 into cosine of 60. That's 1225 joules. Let's restrict it to 2 sig digits. So it's 1200 joules. 2 sig digits because 9.8 is 2 sig digits. That's a work done by gravity, and the expectation is that this work should show up as motion. That means to say the velocity of this block should increase. Coming to part B, determine the work done by the normal force. Work done by the normal force is equal to the same idea. We go from initial to final along the incline, that's the path. And instead of the gravitational force, we use the normal force dotted with dr. But the normal force is perpendicular to the direction of motion. So that's displacement d, and that's normal force. So that's n dotted with d, but that's 90 degrees. So we have cosine of 90 degrees showing up. So it's magnitude of n, magnitude of d times cosine of 90 degrees, which is 0 immediately. We don't have to worry about what the normal force is. So it's 0. Part C talks about determine the change in the gravitational potential energy. The work done by gravity in the case of gravitational force alone, because it is a path independent force, can be written in terms of the initial and final points. So we can, it is defined as negative change in the potential energy due to gravity. So the change in potential energy or the gravitational potential energy would simply be negative of the work done by gravity, which we have already calculated, and that's 1200 joules. Part D, determine the change in the kinetic energy of the mass. The change in the kinetic energy is equal to the work done by all the forces acting on the mass. The two forces acting on the mass are the gravitational force, which contributes to the work done by gravity, plus the normal force, which contributes to work done by the normal force. We calculated the work done by the gravity to be 1200 joules, and the work done by the normal force is 0. So the change in kinetic energy would be simply 1200 joules. Let me stop here or pause here for a moment before I come to the next problem. Problem 2 talks about a roller coaster of mass m moving on the curve described in figure 1. A, a similar curve would be start from point A and it can come down, and that's point A. Doesn't matter what exactly the curve is, and for our purposes, this is point A, that's point E. There is a horizontal ground underneath, and that's height HA, and that's height HE. The velocity at point A is given to be 0. So its velocity at point A is given to be 0. And we are interested in finding the velocity at point E. At any point on the surface, what are the forces acting on this mass m? There is mg acting downward. There will be normal force acting perpendicular to the surface. And in general, there will be friction, but we are given this to be a frictionless uh, surface. There is no spring, there is no force of tension. So we have mass times acceleration is equal to and G plus the normal force. The work done by the normal force is equal to zero because the normal force is always perpendicular to dr. So this is because n dotted with dr at any instant is equal to n times dr times cosine of 90 degrees. The normal force is perpendicular to the displacement on the surface. So that's equal to zero without worrying about what exactly is the magnitude of the normal force. If that is the case, then the only force remaining is the gravitational force, which we know is a conservative force in the sense that it does not depend on the path along which the mass moves. And in that case, the mechanical energy is conserved. That means the kinetic energy plus the potential energy due to gravity at point A remains the same, which means to say that it is the same quantity even if you were to calculate at point E. So that's half times mass times velocity a square plus mg h a is equal to half mass times velocity of mass e square plus mg, the height at e. We are given the velocity at point A is equal to 0. So maybe before I proceed, I should say this is part A. Okay? So the work done by the normal force is 0, and at this point we are working on part B. So just to clarify what part of the problem I'm working on. The initial velocity at point A is equal to 0, and I can rewrite this equation just for insight. Is the change in potential energy of gravity is equal to the change in kinetic energy, which is the energy due to motion at point E. At this point, notice that the mass is going to cancel out, which is the answer to part C, that how does the result depend on the mass. So if mass cancels out, we don't need that information. So velocity at point E is equal to 2 times G times HA minus HE, the change in the height, square root of that. Putting in the numbers, it's 9.8. The change in height is 40 minus 20. And that's equal to 19.6 into 20. And that's 19.8, which is 20 meters per second. 2 seconds. Notice even though the mass of the object is given to us, it does not depend on the mass c, so it is independent of mass in part c. Let me stop or pause the video at this point. This is problem 3 in homework 7. We have a pendulum, which is basically a mass attached with a string to a hinge in the ceiling. So let me draw that as. So that's a pendulum, and when it is vertically hanging down, this will the same pendulum will show up here. So mass M, it's expected to swing along a circle of radius L. So that's L, and this whole length is also the same length L. Let's this point be point A, and the point B at the bottom be called B. There is a difference in height. So let's say if this was the horizontal uh, line, we have height HA here and height HB. So the point is there is a drop in height HA minus HB, which is crucial. Let's also draw a perpendicular line here, which will be helpful in the problem. So that's 90 degrees. That will help us find HA minus HB in terms of L minus L and angle theta. So what is given here is the angle theta, which is 30 degrees. Let's begin by analyzing the problem. What are the forces acting on the mass M as it is swinging? Let me draw the mass M here. That is mg acting downwards. And as it is swinging, there is a force of tension acting along the string towards the center of the circle. So that's tension T. There is no normal force. It is not in touch with the surface. There is no force of friction, and there is no spring. So we have Ma is equal to mg plus the force of tension. Before we can use the conservation of mechanical energy, we have to convince ourselves that the work done by the tension is zero. So the work done by the force of tension is equal to the path along which the mass travels. And at each point along that path, the dot product between the force of tension and the infinitesimal displacement comes into picture. But tension is always perpendicular to the displacement because tension is the radial direction and the displacement is in the tangential direction. So that's equal to zero because T is radial and dr, the, the infinitesimal displacement, is tangential. And we know that in a circle, a tangent and the radius vector is always perpendicular. So this at each instant, at each element of this integral, it contributes zero. Once we have clarified that the work done by the tension is zero, the only other force acting on the mass is the gravity. And gravity being a conservative force, that means that it does not depend on the path along which the mass travels. So we can use the energy consideration between point A and point B to determine the the details of the system. So kinetic energy at point A plus the potential energy at point A will be equal to the kinetic energy at point B plus the potential energy at point B. Or another way of saying it is that the change in kinetic energy between points A and B is the same as the change in potential energy at point B, except they will be in opposite signs because together they have to be zero. The change has to be zero. At point A, we are told it is starting from rest, so uh, this leads to half mva square. Very similar to earlier problem after we have verified that the force of tension is zero. So it's HA is equal to half mv square plus mg HRB. The mass cancels out. VA starts from rest, so that's equal to zero. So we obtain that the velocity at point B is equal to 2 times g times HA minus HB. Very similar to the earlier problem again. So to proceed further, we have to calculate the distance HA minus HB, which is this distance here. So in the diagram, that's HA minus HB. But we are given the length L in the problem and the angle theta. So how do we determine that? So using the geometry, it is clear that this piece here, that's L cosine theta. So we can decipher that the difference in heights HA minus HB is equal to the total length L minus the L cosine theta. That's the projection of the radius L on the vertical direction is helps us calculate the difference in the heights. And that's given to us. So this is L1 minus cosine theta if we want. L is given to us to be 3 meters. And angle theta is 30 degrees. So it's cosine of 30 degrees, which comes out to be minus cosine 30 into 3. That's 0.40 meters. So the velocity at point B now is 2 times, now we have the numbers, 9.8 times difference in the height is 0.40, which comes out to be 2.8 meters per second. And that's the quantity the problem is asking us to calculate. Let me pause here and come back. This is homework 7, problem 4. It talks about a mass sliding down an incline and then coming to a stop after compressing a spring. This is almost identical except for some numbers changing the numbers to what we did in the class in the morning today. We have an incline and a horizontal part of the incline. A mass m slides down. Let's say this is point A, that's point B, and a spring is compressed This is its original position, and after compression, this is the point. So that's point C, and that's the compression X. Let's call that XC as we did in the class in the morning. That tells that the compression in the spring when the mass is at point C. We should first identify the forces and make sure if mechanical energy is indeed conserved or not. We have mass times acceleration is equal to mg is acting on this gravitational force. That is a force due to spring acting. And we have no friction acting on the surface, so there is also normal force acting on the block. So there is gravity, there is normal force, there is no force of tension, there is no friction because it's frictionless, and there is a force due to spring. We know that the gravitational force and the force due to the spring both are conservative in the sense that it does not depend on the details of the path. It only depends on the initial and final points, which leaves us with the normal force. But along the path, the work done by the normal force is equal to 0 because at every instant, so this involves the integral initial to final normal force dotted with the displacement, infinitesimal displacement, but the normal force is always perpendicular to the infinitesimal displacement, and that leads to it being 0 at every instant. Once the normal work done by the normal force is 0, the work done by the gravity and the force due to the spring is accommodated as potential energy. So we know that the kinetic energy plus potential energy due to gravity plus the potential energy due to the spring is conserved. So we say kinetic energy at point A plus the kinetic energy, sorry, potential energy at point A plus potential energy in the spring point A remains the same, which is explicitly written in this form. And kinetic energy point C plus the potential energy due to gravity at point C plus potential energy stored in the spring when the mass is point C. We did this in the class, but just for completeness, let me explicitly show this again. So it's kinetic energy at point A. This is potential energy at point A, gravitational potential energy that depends on the height HA. So height HA is this, plus the energy stored in the spring, which is related to half, it is given by half kx square, where xa is the compression in the spring when the mass is at point A, which is 0. When the mass is at point A, it is not touching the spring at all, so there's no question of it being compressed or extended. So this will be 0. So it's equal to 0 right away. At point B, it has a velocity, so it's mvp square plus the potential energy due to gravity at point B, that's given by the height at point B. If we choose to measure the heights with respect to the horizontal, the height at point B is 0, so that's equal to 0. That depends on the choice of our origin, and it's a convenient choice in this problem to choose it to be 0 at the horizontal. plus half k x b, where xb is the compression in the spring when the mass is at point B. Again, that will be equal to 0. At point C, the mass comes to rest, so it is not going to have any velocity at that point, so that's equal to 0, plus potential energy due to gravity at point C, that's mgHc, but we chose our origin to be on the ground or on the horizontal, so that allows this to be equal to 0, plus the potential energy stored in the spring, which now is compressed by an amount xc, and that won't be equal to 0. The mass is given to be starting from rest at point A. That also allows VA to be equal to 0. So out of 9 terms here, 6 terms are equal to 0. And what we have is mg h of A is equal to half mv square, which is equal to half k xc square. In the first part of the problem, we are interested in calculating the velocity at point B, and we have the information about the height at point A given to us. So part A to the problem, we use the first equality. So mg h of A is equal to half mvp square. Mass cancels out, and velocity at point B is 2 times g times height at point A, which is 2 times 9.8 times the height at point A is, we chose this to be 1 meter. So that's square root of 19.6. That's 4.4 meters per second. Part B requires us to determine the maximum compression in the spring, that's xc. So again, we use mg. We can use the second equality now that we have the velocity known, but we can also equate it to the first one because those are the quantities given in the problem. It's equal to k c square. So compression xc would be 2 times mg times height ha over k. That's equal to 2 times the mass m in the part A that did not contribute. Now it does contribute. It does depend on the mass as far as compression of the spring goes, and that's 9.8 times 1.0 is the height HA, and K is 2 into 10 raised to 4 in the problem. All these are in SI units, so I don't worry about the units. It's 2 times 29.8. So that's 0.14 meters, which is 14 centimeters. And that finishes this problem. I'll pause for a moment and come back. This is problem 5 in homework 5. It is very similar as far as construction goes. Uh, the mass comes down an incline and compresses on a spring, but we have to be a little careful here as to what we can neglect and not. Uh, Sometimes significant digits here does play an important role. So let's do this. So we have an incline, and at the bottom of the incline there is a spring, and this gets compressed. So let's call this point B, and after it gets compressed by a certain amount, let's call that point C. So this amount of compression here will be called X. The amount of distance it falls along the incline. So this could be point A here. This is length L that's given to us. But remember, the change in potential energy is decided by the vertical height. So we are interested in also this height here, which is the projection of the distance along the incline towards the vertical. So if this is height HA minus H of C, it's clear that the distance HA minus HC is equal to L plus X. We have to add this small distance X to it, and then takes the component of that along the vertical. This is sine theta. So that's a detail. And coming to the problem, what are the forces acting on this mass? We have mass times acceleration is equal to gravitational force acts on it. There's a normal force acting on it. There is no force of tension. It's a frictionless incline, so no friction. And there is a force of friction acting between point B and C. So it's a force of friction, which is decided by the Hooke's law. We immediately argue that the work done by the normal force, very similar to what happened in the earlier problems, is equal to 0, which leaves us with two forces, the work or the force due to gravity and the force due to spring, which are both independent of the path along which the mass moves. The energy difference is, or the work done by these forces is completely determined by the initial and final points. That allows us to write the kinetic energy at point A of this mass plus the potential energy due to gravity at point A plus the potential energy in the spring due to at point A is equal to kinetic energy at point C. We are interested in the extreme. We are not interested in point B here in this problem. And potential energy stored in gravity at point C and potential energy stored in the spring point C. The mass starts from rest, so kinetic energy point A is 0 plus mg height at point A plus half k x a squared, that's equal to 0. There is no compression in the spring when the mass is at point A. That's equal to, at point C, the mass comes to a rest because it has already compressed the spring completely. That's again 0. Potential energy at point C due to gravity is mgc plus half k x. Should be xc by the nomenclature we have used, but let's use x here. So it's x squared. So we get our equation, our conservation of energy equation, to be HA minus HC. I move this term HC to the left, and that's equal to half k squared. At this point, we use the geometry that we uh, pointed out right in the beginning, that the difference in the vertical heights HA minus HC is related to the length along the incline by sine of the angle. So that leaves us mg L plus x sine theta is equal to half k x squared. Most of these numbers are given to us, so let's plug in the numbers. So that's 3 into 10 raised to 2 times 9.8 times 2.0 plus x sine of 30 is equal to half of 4.0 into 10 raised to 4 square. I can bring down the 4 into 10 raised to 4 to the left hand side, and this equation takes the form calculate these numbers except for the x. Sine of 30 into 2 divided by 4. And that gives me 0.074 times 2.0 plus x is equal to x squared. Again, I moved the 4 into 10 raised to 4 and divided by 2 to the left. So that's a quadratic equation, x squared minus 0.074 x minus of 74 into 2, so it's 148. I keep the 2 sig digits, so it's 0.15 is equal to 0. So x is equal to plus or minus, and this plus 4 AC, plus 4 times, or maybe I should minus of 4 times A is 1 times minus 0.15. So it becomes a positive quantity divided by 2. And that's equal to 0.074 That's insignificant actually. To two sig digits, the first term does not contribute. So what we get is here 0.074 plus or minus the square root of 0.060, which is 0.78. So it's two solutions here. It's two sig digits, it is minus 0.35 meters and or, or 0.43 meters. This is negative, so that's not a reasonable solution because it's a compression. There's going to be a positive number. So answer is 43, 0.43 meters, which is also equal to 43 centimeters. One should notice that uh, is this really significant? What would have happened if we had not worried about this x? Uh, so let me clarify that here. So if we were to neglect uh, the contribution due to x in HA minus HC, that's a common error that happens. The following is wrong, but it's worth pointing out. In that case, you would have, like in a hurry, you would say that the potential energy, change in potential energy is just L. So you would say this is mg times L times sine theta is equal to half kx squared. So basically what's happening here is that you're dropping this term in the red. And that would make life a lot more easier. We already calculated this number to be 0.74, so we would get 0.074 times L, which is 2.0, to be equal to x squared, and we can calculate x immediately. And that would give us x equal to 38 or 0.38 centimeters or meters is equal to 38 centimeters. To one significant digit, both these answers are right, but 43 centimeters is different from 38 centimeters, even though close, this is different. So this is wrong. So be careful with this slight error that is common. With this, I will stop the solutions here. Thank you.